let's get started. Hello, everyone. Welcome back to Introduction to Semiconductor Devices. So, in this week, we will understand light emitting devices. So far, we have understood the fundamentals. Now, we want to focus on light emitting devices. So, what are the fundamental mechanisms of light absorption and emission? Okay. So, I think we have covered light absorption in some depth. So, we now understand, for example, if you take any material, maybe a semiconductor, right? You have the conduction band and the valence band. So we could think of it as two levels. Okay, so that is what I'm representing here. So I'll represent lower level. Maybe the number of electrons in the lower level. I'll call it as N1, and then the higher level I'll represent it as number of electrons in higher level N2. So I can model the absorption process in the form of a two-level system. For the case of semiconductors, the ground state is the valence band, and the excited state is the conduction band. You could also have atomic absorption, right, in gases. Like in that case, those lower and higher levels or ground state and excited state are not continuous bands, but they're discrete levels, right, in the gaseous species because they're isolated atoms. The energy levels will be discrete. Or it can have various other solids. You can have multiple levels like this. Okay, so the two-level system model, this way of representing is the simplest model of representing a optical system, okay, or optical material. Okay, so on a two-level system, if you have a photon incident, what happens? Well, it turns out that there are three different processes that can happen, and we will study them in some detail right now. The first process is what we call as absorption. So this is already familiar to us. When a photon is incident on a material, it can take, let's say, an electron from the lower state to the higher state. It can take it to an excited state. So what happens in the case of a semiconductor? You will have an electron in the valence in the conduction band and a hole in the valence band. Right? This is what is happening in a semiconductor. Or you could simply just excite an electron in the gas. You take it to higher energy level. This is the absorption process. And the way we can understand absorption process, we try to model it by writing a rate equation for it. So, for example, now I said the population of the ground state is N1 and the population of the excited state is N2. So now if I want to understand what is the rate of, let's say, increase in the, or rather, I'm taking the electrons from the lower state to the higher state, right? So what is the rate of decrease of electrons in the lower state? Okay, so that I can write it as, let's say, derivative of N1 with respect to time. Okay, let's say I'm shining some photons. So how will the population of the lower state change? Of course, it is going to be proportional to the number of electrons in the lower level. So that will be proportional to N1, because if there are no electrons present in the ground state, then there is no absorption that is possible. Okay, so this will definitely be proportional to N1. It is going to be proportional to the intensity of light that you're shining, and that I will represent by a term which I call as U of nu, which is essentially capturing the spectral density. Okay, spectral, let's say, energy density. So basically saying that at each wavelength or at each frequency, how much is the intensity of light that is present. You can have a monochromatic light, that is one single wavelength present, or you can have a broadband range of sources. For example, sun is a broad source, right? You have various wavelengths that are present in the sun, solar radiation. So the spectral density is basically U of V. So if you have this if you have that energy source incident on this material, the rate of change of this is going to be proportional to that. And definitely the number of electrons in the ground state will reduce. So we'll actually put a minus sign. And finally, there is one last term which is called as an Einstein coefficient, because Einstein developed the theory of radiation in 1905. Okay, so he gave this coefficient. So we call them Einstein coefficients. And this particular coefficient is going to be called as Einstein B coefficient and B12. So I'm going from lower level to the higher level. So I'll call it as Einstein coefficient. Okay, Einstein coefficient. Okay, so this is the the coefficient that will capture, and we'll understand that later on a little bit more about it. Okay, Einstein's, let's say, B coefficient. Okay, there's one more A coefficient that will come shortly. Okay, so this is the absorption process. You can also have the opposite process happening, which is emission. Okay, so for example, if you take a semiconductor, I'll take the same, N2 and N1 to represent the populations in the higher and the lower states. Okay, so let's say if you take an example of a semiconductor, you can think of a scenario wherein there are number of electrons in the higher state. Okay, and there are corresponding holes, let's say, in the lower state. What will happen? Well, the electron in the higher state can give up that energy, right? And come down to a lower state. And how much is the energy of the photon that is emitted? Well, it turns out to be equal to E2 minus E1. So the difference in the energies between the higher state and the lower state. Let's say higher state energy is E2, the lower state energy is E1. The photon that is emitted is actually turning out to be E2 minus E1. Okay. So this process is known as spontaneous emission process. This is one of the emission processes. Okay. Wherein without doing anything, just the material, if it has electrons in the higher state, they will simply de-excite and then give you a photon. Okay, this is known as spontaneous emission process, and we can also write rate equation for this. In this case, let's say we are talking about the higher level, right? So let's say what is the rate of change of population in the higher level with respect to time? Okay. In the case of spontaneous emission process, for example, this is going to be dependent on N1 or N2. Well, we need electrons to be present in the higher excited state. So definitely it's going to be proportional to N2. Okay. N2. But there is one more catch here. I mean, what is the rate of emission? Okay. The proportionality constant is actually given by a coefficient which is called as Einstein coefficient again, Einstein's A coefficient. Okay. Einstein's A coefficient. This is basically to capture the spontaneous emission process. So that means spontaneous emission means the photon can be emitted at any random point in time, or so photon are emitted at some instant, at a random instant. There is, there is no way of predicting that. So it's a spontaneous emission process. By the way, it's not going to be one single photon, right? I mean, you can put in, let's say, 10 power 16 electrons in the higher state, and similarly 10 power 16 holes in the lower state. Then any of these electron can de-excite, correct? And there's no way of predicting when a particular electron will de-excite. But when you consider them as a combination of all the electrons, there's a certain, probability that at a particular time they will de-excite and all that. And we will talk about that in a short while. Okay, so this is the spontaneous emission process, which is again the second fundamental process in any material. I mean, it does not have to be only semiconductors. It could be, even gases and so on. Okay. Anywhere you can model a system as two-level system, lower state and a higher state, this laws will hold. Okay. So now the last process of emission is known as stimulated emission. What happens here is, instead of, let's say, instead of just leaving the material to de-excite, you shine a photon. Okay. For example, here I'm showing that we are shining a photon of H cross omega, right? This energy incident on the material. So now what will happen? Suppose it has the same scenario of many electrons in the higher state, and there are corresponding holes in the lower state. Okay. You have this scenario available. Then when this photon is incident, H nu photon is incident, it will cause us emission of a second photon, which is coherent. Okay, what I mean by that is the second photon that is emitted has the same phase and a frequency as the incident photon, and that is why we call it a stimulated emission process. Essentially, the photon is stimulating the emission of another photon. Okay, So this particular mechanism can also be written in terms of a rate equation, and we can say that dN2 by dt is equal to, well, this is going to, the de-excitation in this process is going to depend on, of course, the population in the higher level, which is N2, and it is also going to depend on the intensity of the incident radiation. So we will again write this energy density function, spectral energy density, U of V, and the coefficient that determines this process is called as B21. This is Einstein's again B coefficient, but going from 2 to 1. Okay, so this is, I mean, Einstein's B coefficient, right? We don't need to write that again. Okay, so this is again another type of B coefficient. There are essentially three coefficients, right? Now, the important thing is here emission is coherent, implies the second photon has same phase and frequency as incident photon. Okay. This is a very, very essential phenomena for lasing. You might have heard about lasers. So there's, even the pointers are also having lasers nowadays, right? So all of them are based on this process of stimulated emission. Okay. And spontaneous emission is any tube light or any LED, all of them are spontaneous emission processes. And absorption, of course, you know what is absorption. All right. So these are the three fundamental mechanisms of interaction of radiation with matter. All right. So I just quickly summarize that once again for you. So the rate equations are here. And it turns out that these Einstein coefficients are not really independent. Okay. They are related to each other. If you know one of them, you can find out the other two. Okay. And the relations are given in this box here, essentially telling you that A coefficient is related to the B coefficient. Now, this is this is stimulated emission. This is going to control stimulated emission, and this is spontaneous emission. Okay, and of course, the stimulated emission and absorption are in some sense related because both of them require an incident photon. It's just a reverse process. So there are these, B12 and B21 are related by this relation. Well, this G1 and G2, I mentioned these are degeneracies of the level 1 and level 2. Sometimes you can have multiple levels of the same energy. Okay. So, I mean, for, we can assume to be G1 equal to G2, okay, equal to 1 actually. You can even say it's equal to 1, okay, for simple systems. All right. So essentially B1 equal to B2, B12 equal to B21. This is going to hold for most of the systems unless it is specified, that it is not. Okay. So now, so if you know, let's say B12, you can determine both B21 and A21. Okay. Or any one coefficient is what you need. Okay. And I just wanted to point out one more small thing, which is if you look at this expression A21 and B21, there is a term of frequency here. Everything else is a fundamental constant, but the spontaneous emission seems to increase as a function of frequency Q. Okay, this is very, very important because you might have seen red lasers, green lasers, but it is not very easy to build a blue laser. Okay, because if you know that frequency of red is, red is having a lower frequency, green is having a slightly higher frequency, and when you come to blue, it is still higher frequency, right? So it turns out that as you go to higher and higher frequencies, the spontaneous emission process becomes very, very strong. Okay, so this A21, right? Spontaneous emission is strong at higher frequencies. Okay, and because of which it is difficult to build lasers, because lasers, we want stimulated emission to take place. We want emission to be coherent. We want the photon that is emitted to have the same frequency and phase as the incident photon. Okay, we will actually talk about the construction of a laser in the next couple of lectures. But right now, we just want to say that stimulated emission is essential for laser, and that becomes hard, or that becomes less compared to A to 1, which is a spontaneous emission. You take the ratio is going to scale as frequency Q, right? So that's why spontaneous emission is much more stronger in blue frequencies. Okay. All right. So these are the fundamental processes of emission and radiation. So let me introduce take one more step forward, and essentially this process of emission of photons is called as luminescence. Okay, so we talked about emission, but we just want to understand it in a greater detail. For example, now let's consider a scenario wherein you have these four electrons which are at the edge of the conduction band. Okay, and then there are these four holes which are at the edge of the valence band. So what will be the frequency that is emitted? Okay, so if I want to, if I ask you, let's say, to draw the spectral, intensity, or rather, spectrum of the emission process, for example, I want you to draw. So this is, I want, let's say, energy or wavelength, E, or you could even call it wavelength. It doesn't matter. Let's say, you can, interchangeable, you can calculate that. And I want to calculate the intensity here. Okay. For our purposes, maybe, since we are talking of semiconductors, let's just talk of right now energies. Let's talk in terms of energies. Okay. So I want you to draw energy versus intensity. This is a spectrum. Okay. So at which energy will you have strong emission of photons? Well, will you have, let's say this is a Eg, okay? This band gap, I will take it to be Eg. Will you have emission at the Eg? Or rather, if when you have emission, let's say I'll put Eg here for reference. Now, will you have emission at energies much lower than Eg? Well, there are no states available. For example, if you had electrons at this state and this some virtual some states in between, then you could have emission in between that. But since we don't have any states, the smallest energy that you could emit is at Eg. Okay, so there should not be any emission. It turns out that it will not be exactly easy, but it will be growing in this fashion. As you grow higher, the intensity of the emission increases. Now, the other question is, let's say you have a scenario, you somehow are injecting electrons into the conduction band or in upper state, and then you're injecting holes into the lower state. Okay. So let's say you manage to inject electron at a higher energy. Now we said that as you go deeper into the conduction band, we can represent, we know that this is having a higher energy, right? And this is again higher energy hole. So can this electron recombine with this hole and give you a higher energy photon? So the question is, can you get h nu greater than Eg? Is this possible? If so, how much energy is possible? Because we know that there are a lot of energy levels in here. There are a lot of energy levels in the bottom here. So will it emit at all frequencies or all energies or at a particular energy? The answer to that is, it turns out that you will have emission only centered around Eg. Okay. So I'll just put it in blue. So this will be your emission process. Okay. The reason is, even if you have an electron which is in a higher energy level, for example, here, right? Even if it is here, what happens is this electron loses its energy by, we call it thermalization, or, we also call it as relaxation. So it relaxes here. So this is called as relaxation. What essentially is happening is it loses its energy to the lattice and then comes down to the edge of the band. Okay, because that's where that's the lowest energy state possible, and it will try to come down to the lowest energy state. Similarly, a hole will relax to the lowest energy state for the holes. Remember always, this is increasing energy for electrons, in this direction, energy increases for electrons, right? Whereas for holes, this is the direction of increase of energy, right? So if the hole loses its energy, it will come closer to the valence band edge. So this way it relaxes. Okay, this is again a relaxation process. It turns out that the excited carriers or high energy carriers will relax and come down to the edge of the band. Okay, so this is a simplistic picture, but finally, what happens is this: there is, the emission process has a certain energy, you know, bandwidth, the full width half maximum. You could also call it as full width half maximum. So there is a center wavelength, and then there is a spread around that. Okay, so it turns out that this spread is very, very important. If you have any LED emission, this spread is going to be about 20 to 30 nanometers. That's a typical number. So if you have a blue light LED, you'll see that it's predominantly blue, or a green LED. So predominantly it is going to be maybe tens of nanometers width. Whereas if you come to lasers, red laser or a green laser, they are very, very coherent. That means they're monochromatic in a sense. They'll just have a couple of nanometers or 1 nanometer or so. If you have gas lasers, they'll actually have even lesser width. So you want it to be as pure laser as possible. You know, you could relate it maybe, in a way to, if you take signals and systems courses, you'll talk of sine waves. A pure sine wave is a perfectly monochromatic wave. I mean, it has a single frequency. But then if you introduce some distortions in that, then the width of the line, the sine wave becomes broader, right? The frequency becomes broader rather. Let's say if you apply a window to that sine wave, okay? When you apply a window, essentially you're broadening the sine wave because there is it's fundamentally related to the uncertainty actually, okay? So there's a certain, anyway, we don't need to get into that. That's a distraction. So I just wanted to point out that this is the emission. This is the way that emission happens. All right. So let's just try to do some, just introduce some numbers. So we said that already. The population in the higher state, right? dN2 by dt is going to be dependent on Einstein coefficient, A21, spontaneous emission, right now, okay, and N2, right? And that's it. So if you want to have stimulated emission, we have to create some necessary conditions for that. And we will talk about it later. Right now, simple spontaneous emission, because we want to talk about LEDs. Okay. So A21 minus A21 N2. So if you solve this equation, the solution turns out to be N2 of t is going to be N2 of 0 and exponential minus A21 times t. Okay. So, I mean, if you look at it, I mean, you immediately recognize that this is something similar to the rate equations we have seen, right, before. So, rather, the exponential decays that we have seen. So, you could write it as exponential minus t by tau, okay, and this, okay, I'll call it as tau radiation, okay. So, tau r, which is the lifetime, radiative lifetime, okay. So, this is going to be equal to 1 over A21. This I will call as my radiative lifetime. Essentially, how much time it takes on an average for a electron to de-excite and emit a photon. Okay. So this is how the radiative decay happens. But as the name indicates, when there is something called as a radiative decay, there's also going to be something called as non-radiative decay. What is non-radiative decay? Well, your electron, instead of emitting a photon, it could simply, just lose its energy to the lattice, right? Lattice essentially means it's just lattice atoms are there. They are vibrating, right? At whenever temperature is not zero, they're vibrating. So, in a sense, your electron can lose its energy to the lattice vibration and just come to the lower state, right, and get captured. So that is called as a non-radiative decay process. So non-radiative decay, electron loses energy to the lattice. Okay. So this is also going to be present, of course. It's never going to be that only radiative decay is present. We would like to have radiative decay to be more because we want photons to come out. Okay. If when you say non-radiative, it is losing to the lattice, that means, we say phonons, phonons, it's essentially heat. It's heating up the semiconductor, which we don't like. Okay. So we can write a rate equation for this as well. We can add a term into this. So the upper state rate of change of population is going to be minus N2 divided by tau radiation. And then there is another channel which we call as tau non-radiation, non-radiative channel. Okay, these two channels are going to be there always. We will see when we actually we'll talk of LEDs. We would like to have a radiative channel to be more efficient, or rather more rather. Okay, so if your tau radiation is much smaller, let's say if your tau r is smaller than tau nr, what happens? Well, when tau r is small, then this is going to be large. Okay, basically this is going to be large. That means light emission is efficient. Okay, so in this case, what happens is light emission is efficient. Okay, in a way we are saying that A21 is large. Okay, indirectly. Okay, so you want it to quickly emit light. You want to quickly emit photons. If you consider other scenario where tau r is much greater than tau nr, what happens? Essentially, it means that it's taking more time for an electron to emit a photon, but instead, before that, it will actually non-radiatively decay into phonons. Okay, so this here actually light emission is inefficient. Okay, so heat is generated. Heat is generated as byproduct. Okay, which is undesirable for us. Okay, unless you're trying to heat something. Okay, we don't like non-radiative decay processes. All right. So these are essentially the fundamental. This is a fundamental description of how the radiation happens. Before I stop, I just quickly wanted to show you two types of emission or luminescence. Luminescence, I said, is basically emission of a photon. We can have photoluminescence, which is essentially, you shine a photon. Like for example, I take a semiconductor which has a band gap of 2 eV. I shine light which has an energy of 2.5 eV, and then I'll make it emit at 2 eV, right? If I have a band gap, for example, okay, the band gap is, let's say, in this case, 2 eV. I can shine any photon of a higher energy. For example, in any, I'll say E pump, which is I'm pumping the semiconductor with high intensity of energy of greater than 2 eV. E pump is greater than 2 eV. When I do that, I'll basically create lots of electrons and holes, right? When I do that, they will relax to the band edge and then emit a photon at 2 eV, right? So basically, this process is known as photoluminescence process. So basically, it is re-emission of light after absorbing a photon of higher energy. Okay. So this is known as photoluminescence, just indicating that you're using light to cause luminescence, higher energy. So the luminescence is going to be at the band edge. And an example of that is shown in the graph here. So in this graph, what you're seeing is energy versus luminescence, how much strong the light is. And you see, two things. One is, this peak, which is characteristic of the luminescence, PL, we call it, okay, photoluminescence. And you see that, it's a low temperature, by the way. So, and it's gallium nitride sample. So the band gap is about 3.3 eV, 3.3, 3.6 eV here, 3.547 eV, I think here. Okay. So anyway, there's a small difference because of the temperature. So you have the PL, which is, I talked about this sort of a peak, which will occur. Emission is occurring around the band edge. And then what happens to absorption? We've already discussed absorption. So this optical density is a measure of absorption. Okay, this is basically a measure of absorption. Okay. So what you see is any photon which is higher than the band gap, it will absorb. Okay. This is a logarithmic scale, by the way. You should not, you should not wonder why it's not steeply increasing. Since it's a logarithmic scale, we quickly see an increase in the absorption, and then it's saturating. After some time, it doesn't, it doesn't have any more. Yeah, it saturates. Okay. So this is absorption process, whereas the photoluminescence is happening around the peak. This is one of the ways to characterize a semiconductor's band gap. Okay, you can do this experiment at various temperatures. This is at 4 Kelvin. You could do it at room temperature and see the shift in the PL. That tells you how the band gap is changing with temperature. Okay, this is one of the practical ways of measuring band gaps. Okay, so this is one of the process. There is another process which we call as electroluminescence. Luminescence, which essentially means you are having emission of photons by supplying current. So I supply my electrons and holes into the semiconductor, and then I'll make it emit light. That is known as electroluminescence process. For example, your lasers, your LEDs, all of these are electroluminescent devices. Okay. So again, the same characteristic peak. Okay. This time, this is a different material, gallium arsenide. Current supplied is 1 milliamp and temperature is this. So band gap is 1.42 eV. So you get an emission around that, around 1.42 eV. There is some emission. Okay. So these are quite clean spectra, but there are many more things. By looking at the shape of it, we can infer a lot of information about the material. So if you do research in some of these things, you will actually analyze these spectra in more detail, and you will study why all of that is happening. All right. So this is the fundamental process of luminescence. So with this, I hope I have explained the basic phenomena of how radiation happens in a semiconductor. Okay, it's much more general, but semiconductor is what we are talking about in this course. So radiation in semiconductors. All right. So with that, I would like to stop this video. In the next video, I'll talk about various materials for optoelectronics rather. Okay. All right. I'll see you in the next video. Thank you very much for your attention. Take care. Bye.